really delighted and very happy that Professor Peter M. Hines from the University of York agree on presenting something really very interesting. And I think this is a kind of topic uh, our whole mathematical community is very much aware of. It's about something related to Collard's conjecture, but today Peter Hines is going to discuss something related to on Conway's proof of undecidability in elementary arithmetic. So over to you, Peter.
Okay, well, thank you very much, and also thank you for the invitation to give a talk. It's genuinely a pleasure. Okay, so as the title says, what I'm talking about today is Conway's proof of undecidability in elementary arithmetic. Now, before I start, there's a series of references to go along with this. What I'm talking about today is category theory through and through, but at the same time, I try and reserve the actual category theory for category theory conferences. So if you're interested in a sort of full categorical logic approach to things, that's the first item on this list, which is to appear in about a month's time. Today's talk is mostly based around the third one on the list here. And yeah, so a little bit of light reading, as it says. Okay, so what I'd like to start with is a description of a programming language. It's due to John Conway, and he called it Fractran, which is of course a pun on Fortran, formula translator. Well, this is the fraction translator. And the nice thing about this is that it's next to impossible to write a syntactically incorrect program, because all a program is a list of positive rational numbers, fractions. Now, the input to this is simply a natural number. Positive natural number, you can use 0, but then the behavior becomes somewhat uninteresting. And all that happens is you take your natural number and you try and multiply it by each of these fractions in turn. And you keep doing this until you arrive at a whole number. And then this becomes your new natural number. You return to the start of the list and you do the same thing again. So you've got a notion of conditional looping. You keep going through, you multiply until you find a whole number, you return to the start of the list, and then you continue the process. And you keep doing this until you arrive at the end of the list, even assuming that the list itself is finite. There's two possible options for the output, either the final value of n at which you arrive, your final natural number, or alternatively the trace, so the sequence of values that your natural number takes on during the execution. Okay, so it's a slightly bizarre programming language, and really the question should be, what can we do with this? And the answer is, well, what can we do with this? Whatever we like, because it's computationally universal. So we can use it to compute partial recursive functions, or we can use it to simulate a Turing machine, or if into that sort of thing, we could use it to model untyped lambda calculus instead. Now, because it's computationally universal, of course, it's subject to the halting problem as described by Alan Turing, which tells us that given a computer program, there's no way of predicting, even in theory, whether it's going to halt, whether it's going to terminate on a given input. We can in particular examples, but in general, it's undecidable, even in theory. Now, John Conway gives this rather nice example. If you go online, you can see him doing this. He simply writes it out on a blackboard. I don't know if he's doing it from memory or actually calculating these fractions as he goes along, but this program fails to terminate. And if you look at the trace, you see why. So the trace, you simply get a list of natural numbers. And if you look at the powers of 2 that you get in the sequence here, what you get are 2 to the 2, 2 to the 3, you get 2 to the p, where p is prime in order. And these are precisely the powers of 2 that appear in the series. Now, when you're looking at this sort of thing, obviously certain natural patterns. So for example, you might ask, what do we get if we take our list of fractions and reverse it? Alternatively, if we take every fraction and look at its reciprocal, or maybe do both. So there's various natural transformations that we can apply to programs like this, and we might ask, how does it actually behave when we do so? In order to answer questions like that, we need to understand why this works as a programming language. Why does a list of fractions interpret as a computational system? And the answer is a very mathematical answer, which is the fundamental theorem of arithmetic. So every natural number greater than 1, of course, admits a unique prime decomposition. So we can think of it as an infinitary product where only a finite number of terms in our product are not 1. So we look at the powers of the primes, a finite number of these are non-zero, and we can think of these as registers in our computer. So John Conway, he works with a model of computation known as the universal register machine. And what we see then, when we multiply by a fraction, we assume it's in its lowest form for simplicity, we have a conditional. So the conditional statement is, if we divide by this denominator, do we get a whole number? So we can ask ourselves, is the power of 3 at least 3? Is the power of 7 at least 1? If these conditions are true, what happens is that then we increment other registers. So we take the power of 5 and increment that by 3, the power of 11 and increment that by 2, and then we branch back to the beginning of our program. So we've got conditionals, we've got increments, and we've got branches. And finally, our conditionals are resource sensitive in that when you make a test, if you're successful, well, you take something out of the register to check and you don't put it back. So you decrement the register by that test value. So what we have here is we've got conditionals, increments, decrements, and branching, which really puts it almost as a low-level assembly language. We have enough for computational universality, and we have enough structure that actually we can, if we're that way inclined, write reasonable programs within this programming language. And of course, taking reciprocals, well, all that does is interchange our conditionals and our decrements with our instructions and our increments. Okay, so far, so fun. But really, the interesting question is, what was John Conway's motivation for this? And this, of course, came out of his work, as the title of today's talk suggests, on undecidability in elementary arithmetic. So his famous unpredictable iterations paper in the Boulder Number Theory Conference in 1972. This demonstrated computational universality and therefore undecidability because of the halting problem, based on simple iterative problems on congruential functions. So congruential functions are key to this, and they're simply functions that are defined in a piecewise linear manner on modulo classes. So we take the natural numbers, we split them up into a series of modulo classes, and on each distinct modulo class, we apply a distinct linear map. It takes natural numbers to natural numbers. These don't have to be complicated things. We could simply take the natural numbers and split them up into the odds and the evens. Every even number, we could just divide it by 2. Every odd number, we could multiply by 3 and add 1. And if we were to do that, a remarkably simple congruential function, we would instantly arrive at one of the most notorious problems of mathematics, which is, of course, Collatz' 3x plus 1 problem. Now, I call this notorious simply because it has wasted so many people's time, it's quite incredible. There's the feeling that because it's simple to state, it should be simple to prove. It's not. I think we all know that it's not, and we also know, thanks to John Conway, that it is quite possibly undecidable. It sits right in the middle of the framework he gave to demonstrate undecidability within arithmetic. But what I'd like to talk about is not the 3x plus 1 problem. It's about what John Conway described as his motivation. So this is another conjecture of Collatz. It was published in, sorry, it wasn't published. It was from his unpublished notebooks in 1932. So somewhat predates the 3x plus 1 problem. And it's based around this congruential function that John Conway describes as the amusical permutation. So here it is. It's got infinite, well, the conjecture is anyway that it has infinite orbits. Collatz conjectured that the orbit of 8 is infinite. And John Conway described this as the best candidate we have for a statement in mathematics which is true but unprovable.
Mm.
The precise term he used was probvious, which was a contraction of probabilistically obvious. So he gives a probabilistic argument as to why this conjecture is true and points out that the probability of an error appearing in a published mathematical proof is far greater than the small probability that this conjecture is false. And if we take a plot of this, if we plot n against gamma to the n of k for some fixed k, including 8, well, we best be taking a log plot because we have exponential growth. Now, if we take a log plot, we have this graph here, which is decidedly V-shaped. And well, by the time we get up to 200,000 iterations, we're around 10 to the 5,000. In a log plot, it is approximately rising in a straight line. And well, this was John Conway's motivation for his proof of undecidability. Okay, well, this next slide isn't really anything to do with the rest of the talk, but if I don't present it, people are going to spend the rest of the talk wondering why it's called the amusical permutation. So here's John Conway's motivation. Now, first of all, he observes that there's 12 notes in a musical octave, and a musical octave represents a doubling of frequency. So 12 steps of either gamma, the amusical permutation, or its inverse approximately doubles a number on average. Now, this feels slightly paradoxical that either a function or its inverse doubles a number. So let's have a look. If we choose some natural number here, we have a finite interval where it's decreasing, and assuming the conjecture is true, infinite intervals where it's increasing for either gamma or gamma inverse. So simply because we're working in the infinitary setting, both gamma and gamma inverse can approximately double a number on average. Now, okay, so far so tenuous, but this expected doubling is not exact. If you run through the figures, the amusical permutation doubles by a factor that's almost 2 but not quite, and similarly for its inverse, almost 2 but not quite. But if you're working with musical scales and musical theory, if you want to know the notes that lies in between two notes, what you do is you take their geometric mean. You multiply the two together and take the square roots. And there you do indeed get the exact doubling. And even more so than that, if you're more heavily into your musical theory, you're probably aware of the circle of fifths. So the fifth interval is dividing an octave into a 3⁻² ratio. And the circle of fifths is increasing by a fifth modulo your octave each time. And you cycle through all your notes in the octave until you arrive back at the same note, or rather doubled, an octave higher. But you don't quite arrive back there if you're working with a pure scale simply based on ratios of frequencies. You have what's known as the Pythagorean comma, though it appears to be known by the Mesopotamians and the Babylonians before Pythagoras, which is frequency ratio of 3⁻12 over 2⁻19. And we see that the expected doubling of the amusical permutation is actually ratios of the Pythagorean comma. So as Conway puts it, there really is a close connection with music. And I've been trying to explore further where this goes. There's been surprisingly little written about it, and we currently have a final year student in York doing a project on the Pythagorean comma. And there's one last point to address, which is Conway calls it the amusical permutation rather than the musical permutation. And he says that the series ascends by a fifth modulo octaves. It does not sound very musical, which if you go to Wikipedia, for example, and look up, say, the circle of fifths, you discover a large number of classic works of music that are precisely based on the circle of fifths. One moment. For example, okay, okay, I'm not hearing that, so never mind, maybe at the end of the talk. But the point is, he says, it's always amused me to call it amusical, and this is actually giving a hint to what he really meant. He's always fond of puns and word plays, and apparently what he really meant was this is the amusing musical permutation. So yet another contraction, simply like obviously. It's precisely a musical permutation. Okay, well, that's nothing to do with the rest of the talk, but it needed to be addressed, otherwise people would be wondering about it. What I am talking about is we've got these two conjectures, Collitz's notorious problem and the original Collitz conjecture, which is also a fascinating thing. We might not be able to prove or disprove them. We certainly couldn't prove them to be undecidable, simply because a proof of undecidability would be a proof that no counterexample existed. So the question is, can we understand them better, simply by interpreting them as Fortran programs or similar? Unfortunately, no, we can't, because, well, Fortran programs, they do implement congruential functions, but congruential functions of a very special form. Congruential functions whose additive part is 0. So we've ruled out his motivating examples, and the point of the talk today is saying, well, if instead of looking at very simple assembly-like procedural languages, if we look at other areas of, say, theoretical computer science or logic, pure mathematics or category theory perhaps, do we find congruential functions turning up there instead? And can we find even the examples that motivated Conway? And well, the answer is yes, otherwise the talk would finish now. So let's carry on and do precisely that. And our starting point is going to be looking at the domain of congruential functions, which is taking the natural numbers and we're dissecting it into disjoint modulo classes. So this gives what Paul Erdős and company called an exact covering system, which is precisely an indexed family of modulo classes whose union is the whole of the natural numbers, and the intersection of any two is empty. And all I'd like to do is take this simple definition and characterize it in terms of elements of a monoid rather than in terms of sets, intersections and unions. So I'm going to look at a monoid of functions on the natural numbers. Every modulo class, trivially, it's countably infinite and in one-to-one correspondence with the natural numbers. So I'm going to look at the algebra of the functions that exhibit this correspondence. So, well, how do we exhibit a correspondence between n and an plus b? Well, it's kind of trivial. We take every natural number n, multiply it by a, and add b. That's all we're doing. This is trivial. So if we've got pi, takes n, maps it to ain plus bi. We have two of these, pi and pj, or the intersection of their images has to be empty, and the union of their images has to be the whole of the natural numbers. Okay, well, that's just a minor rewriting of the set theoretic considerations. So let's continue and describe it more algebraically. And what we're going to do in order to do this is we're not going to work with functions, we're going to work with partial functions. And as well as allowing our functions to be partial, we're going to insist that they're injective. So fx equals f prime x, well, that only happens when x equals x prime. And we also need to add in, provided that both fx and fx prime are defined. And if we have partial injective functions, well, we also have generalized inverses. So fx equals y, then f star y equals x. So it's like a group theoretic inverse, but we're working with possibly partially defined functions. If our functions are globally defined by bijections, well, this becomes precisely the inverse in the group theoretic sense. Given two partial injective functions, we've got a partial notion of summation as well. So our sum is defined when the domains are disjoint and the images are disjoint. Then our sum is simply the set theoretic union of our two functions. So f plus g of n, well, if fn is defined, it's fn. Similarly for gn, and it's undefined otherwise. So if we have this pj maps n to ajn plus bj, well, we've got its generalized inverse, which is only defined on this modulo class ajn plus bj. We subtract bj and then divide by aj, and it's undefined otherwise. And then we can characterize the conditions for an exact covering system entirely algebraically. So first of all, if we take the whole of the natural numbers, map them to a modulo class, then map back to the whole of the natural numbers. That's the identity. If we take the whole of the natural numbers, map them to a given modulo class, map an entirely disjoint modulo class back to the whole of the natural numbers, well, the domain of one intersects the image of the other is empty, gives the composite here as the identity on the empty set. And then finally, we need that the elements of our exact covering system cover the whole of the natural numbers. So we take a modulo class, map it to n, map it back to the same modulo class. We get a partial identity on that modulo class. And then we take the sum of all these partial identities, giving us the identity on the natural numbers. So we get 3 defining conditions for an algebraic structure. And the question is this familiar? And the answer is yes, it is. And not only is it familiar to my specialist fields, it's familiar in an awful lot of other specialist fields as well. So if you're into, say, semigroup theory, you would know this as Never and Perot's polycyclic monoid. If you're into C-star algebras, you would probably be talking about the Kunz algebras. The logicians, they know it as the dynamical algebra. Well, the nth dynamical algebra rather, because we have possible different numbers of generators. We see it turning up in automata theory, even a recent PhD thesis in linguistics. And I like to judge how fundamental a mathematical structure is by how many times it's rediscovered. And this one is certainly up there in the top 10. So I'm talking about computational interpretations today. And what we see is dynamical algebras turning up in, well, a vast range of places, starting from the late 1980s, computationally universal models of logic, lambda calculus, computing systems, etc. And here's my claim. We're going to see the precise examples that motivated Conway when we start considering the category theory behind these models of computation. So it's not really going to be about the models of computation themselves. I'm not going for a full-on explanation of those. I'm simply talking about some of the structure that lies behind these models. So here's an example. It's a model of logic. It's particularly relevant because propositions are modeled by functions on the natural numbers. Precisely, they're partially injective functions, and conjunction, and that's just defined in terms of the dynamical algebra. So it's a 2-generator dynamical algebra, and it's based on the odd-even dissection of natural numbers. So we take P, which maps a number to the double. We take Q, which maps n to 2n plus 1. Maps the whole of the natural numbers to the even and the odd. And conjunction of 2 terms is given by conjugating these terms by these generators of the dynamical algebra. Or more simply, what we do is we take f and g and we rewrite them not on the whole of the natural numbers, but we replicate them on the even numbers and the odd numbers respectively. So it's like Hilbert's Hotel for functions rather than for simply numbers. We're taking 2 functions, we're not losing any information, we're simply replicating their behavior on the even and the odd numbers. And when we do this, what we get is a monoid homomorphism. So a homomorphism from 2 copies of this monoid on the natural numbers to a single copy. And then we discover a property which is somewhat unusual for a conjunction, which is it's not associative. And this is a general property. Paper from 2016 tells us that if you've got any injective homomorphism from 2 copies of a monoid to a single copy of a monoid, assuming the monoid is non-abelian, this can't be strictly associative. Bracketing matters. But it doesn't matter very much, because what we do have is a single bijection on the natural numbers that maps one bracketing to another bracketing by conjugation. So we call this the associator because it's about associativity. And for example, we can take a left bracketed A and B and C and map it to a right bracketed A and B and C simply by conjugating by this associativity isomorphism. And rather neatly, this is a congruential function. It's a bijection on the natural numbers, so it's a member of the symmetric group on N, it's congruential. So we can ask a question which is probably not been asked before, which is, what happens if we take this unique associativity isomorphism for a conjunction from linear logic and ask a collapse-like question about it? So, does it have any finite orbits, or can we characterize the finite orbits? And well, the answer is actually rather disappointing. We've got an even-odd split. If something's even, we double it. That's going to diverge to infinity. If it's odd, well, it's either going to decrease it and give us another odd number, or it's going to give us an even number. So any odd number is simply going to decrease until it arrives at an even number and then disappear off to infinity again. So all orbits are infinite apart from the single fixed point at 0. So we see congruential functions appearing in models of logic in a very fundamental way because we need them to deal with associativity, but they're not interesting. At least they're not interesting in terms of collapse-like problems, but in terms of other topics in mathematics, they can be interesting. So let's have a look. Richard Thompson's group F, I understand, is a big deal for group theorists. And in 1996, Patrick de Hornoir paper, The Structure Group for the Associativity Identity, gave a rather nice connection. Well, it was kind of folklore beforehand, but he gave it precisely. He gave a rather nice connection between rebracketings and Richard Thompson's group F. And if we translate what he had in this paper into our setting, well, what we get is a generating set for Richard Thompson's group F. And we have a key condition on our infinite generating sets that if we conjugate one generator by another generator, we lower the index of that generator by 1. So let's say we have x0, our first generator. That's our associativity isomorphism. x1 is the identity and the associativity isomorphism. x2, identity and associativity. Well, if we conjugate x2, or indeed xj for any j, by alpha, what we get is we're rebracketing. So we're bringing two identities together and arriving at identity and identity. But this and is a monoid homomorphism. So identity and identity is simply the identity. And what we've done is we've lowered the index of this generator in Richard Thompson's group by 1. So we have the generators of Richard Thompson's group, we have the defining relations, and we have a result of Matt Bryn that says Richard Thompson's group doesn't have any non-abelian quotients. So this is a homomorphic image of Thompson's F, but actually, because we know it's non-abelian, it's isomorphic to Richard Thompson's group F itself. And simply using the interpretation of Girard's conjunction, these generators are simply replicating this associativity isomorphism on modulo classes, 2n plus 1, 4n plus 3, 16n plus 15. The pattern here is kind of obvious. And the neat point here is that, again, we don't have any non-trivial behavior under iteration. All our orbits are either infinite or fixed points. Okay, so it's kind of fun to be sort of mixing concepts from different fields.
Professor Peter, excuse me.
Good day.
What was fixed in this particular map?
Oh, in this particular map, it's fixed everywhere it's the identity. So outside of each of these modular classes, it's fixed.
Okay, okay, thank you.
And also you've got the additional single fixed points that comes from the fixed point from alpha. So if I go back here, alpha has got a fixed point at 0.
Okay, okay, thank you.
Yeah. Okay, so I mean, just to say, please do sort of jump in with any questions. I'm here to be understood essentially. Okay, so one final point about this is that this presentation of Richard Thompson's group, although it's the most natural one, it's not minimal. And we know that the first two generators in the sequence are enough to generate the whole group. So we can give them explicitly here, 2 bijections, generate a copy of Richard Thompson's group F. And if we look at composing, and these give all possible ways of rebracketing our composites of conjunctions. Unfortunately, we don't find interesting behavior under iteration, which is a shame because it feels like we're almost there. In fact, we are almost there. We're just sort of taking things too rapidly. So what we should be doing is saying, well, rebracketing, let's not be too hasty. This is a two-part process. What happens when we rebracket is we're deleting a matching pair of brackets somewhere and we're inserting a matching pair of brackets somewhere else. So the claim is that once we start considering how we do this, we are going to see precisely the operators of Collatz that motivated Conway. So in terms of how to proceed with this, first thing we need to do is give a slight generalization of Girard's conjunction. So we've got this binary model of conjunction and it replicates two functions on the even numbers and the odd numbers. We're going to do the most obvious thing in the world here and give a ternary analog. So instead of replicating A and B on the odds and evens, we're going to take A, B, and C and replicate them on the congruence classes modulo 3. Remainder 0, remainder 1, and remainder 2. And well, we're going to start drawing these things as trees because in a moment, I'm going to be plugging trees together. But first, well, we can do this in general, having done it for 2, 3, we can carry on, do it for 4, 5, etc. And the kth unbiased conjunction, well, what we do is we take F0, F1, all the way up to Fk minus 1, and replicate these on the congruence classes modulo k. So replicate them on Kn, Kn plus 1, Kn plus 2, etc. And I'm going to draw these as very simple trees. So simple trees, we've got a root, we've got leaves, and no non-trivial branchings in between the two. And then I'm going to start plugging these together. And this is going to give us a structure known as an operad. And well, even though these turn up a lot in category theory, even in category theory conferences, you have to give the definition and explain precisely what they are. So here's the formal definition, which is we've got an indexed family of sets. These are disjoints and their elements are operations. So if we have something in, say, H3, we say it's got arity 3. And if you've got an operation of arity 3, there's 3 different compositions associated with it. Draw these as circle 1, circle 2, and circle 3. We've got an identity in H1, and then we've got these fairly hideous looking axioms just here, which I can't remember them, and I'm pretty sure that nobody else can either. Every time I come to write them down, I have to draw pictures instead. So let's just go straight with the pictures, because ultimately operads are a very, very graphical thing. We draw them as trees, and the first part of our axiom says that composition is associative. F composed with G composed with H is the same as F composed with G composed with H. The only reason the axioms look complicated is because we have to deal with the re-indexing of the leaves of the trees. The second part of the axiom says that parallel composites commute. So if we take 2 distinct trees, plug them onto leaves of another tree, it really doesn't matter the order in which we do this. So the most simple thing in the world, made slightly complicated looking by the fact that we like to write our axioms out in a line rather than simply draw pictures for them. So I'm going to do this with elementary. Hello.
Excuse me. Professor Peter, can you explain what does this subscript of the O 3 and 2 what they are indicating?
Okay, these are simply the axioms. So I'll give a concrete example of something that they interpret as shortly, but formally we simply think of them as axioms in the same way as composition in a group, if that makes sense.
Okay, so particularly if I see the first operator, so this O3 3 indicates that the each branch is going to be placed at the 3rd position. This is what it does mean?
Yeah, precisely. Yeah.
Yeah. Okay. Okay.
Okay.
Thank you.
That's okay. Cool. Okay. So the nice thing about this is that we can Well, a good example of this is simply plugging together functions, or homomorphisms, as I'm going to do in this case, because I'm going to take a tree and I'm going to interpret it using these generalizations of conjunctions. So I don't know if people can see my mouse pointer, but up here we've got a threefold branching. So I'm going to interpret that as our threefold conjunction. We've got a binary branching. This is a twofold conjunction, and another binary branching giving us a twofold conjunction again. So we plug these things together simply by substitution, and we arrive at a monoid homomorphism from 5 copies of the symmetric inverse monoid on the natural numbers to a single copy. And then we've got a kind of important question, which is, do the trees uniquely determine homomorphisms, or can 2 distinct trees determine the same homomorphism? Well, if distinct trees determine distinct homomorphisms, we've got a notion of freeness. So it's a big thing in the theory of operads, which is simply the formal operad of rooted planar trees. And if we freely generate using one operation of each arity, so one tree with a certain number of leaves, well, we get a freely generated structure. And this is the claim, that this operad of generalized conjunctions and this notion of substitution is freely generated, so it's isomorphic to our formal operad, which is so well studied and used in so many different fields. And in order to prove this, we need to give an explicit description of the homomorphism implemented by an arbitrary tree. So again, let's use the same tree as an example. This gives the homomorphism from 5 copies of a monoid to a single copy. And if we apply this to, say, F0 all the way up to F4, each of these FJs is replicated on some modulo class within the natural numbers. So if we say, look at F3, 0, 1, 2, 3, this is replicated on the modulo class 12n plus 10. So we can prove that by an inductive argument, of course, but really what I'd like to be able to do is simply take a tree and simply write down these numbers, 12 and 10 from the tree. And actually doing so is the simplest thing in the world, because all we do for a given leaf, we look at the path from the leaf of the tree to the root of the tree. So to find our multiplicative coefficient, 12, we simply multiply together the number of branchings at each step. So 3, 2, 2. 3 times 2 times 2, 12. To write down the additive coefficient 10, it's even simpler. We number our branchings 0, 1, 2, 0, 1, 0, 1, and we write down 2, 1, 0, the branching that we took on the path from the leaf to the roots. And then our additive coefficient is 210, but it's not 210 in decimal, because what we've done is we've written it down in a mixed radix counting system. So where the base used varies according to the column. So if we've got, say, branching x out of total of y, where we number x between 0 to y minus 1, then we have the base y and the value x in that column. So 210 in decimal is simply 10. And in a rather neat historical coincidence, the first person to study mixed radix counting systems formally was Cantor himself. Okay, so we've got a neat correspondence, which is we've got rooted planar trees. Well, they are, of course, uniquely determined by the addresses of their leaves. The addresses of their leaves uniquely determined by counting system, ordered exact covering systems on the natural numbers. So each distinct tree determines a distinct ordering exact covering system, determines a distinct homomorphism. So what we get is our operad of generalized conjunctions is indeed freely generated. And also each tree is going to determine a distinct realization of a dynamical algebra. What we're interested in is not just the homomorphisms. We want to know how to map between them, how to map the result of one to the result of another by conjugation. So to find these, again, well, we'll do this by example. We take 2 trees with the same number of leaves, and we write down as a list, each leaf determines a modulo class. Taken together, these give an exact covering system. And we map one modulo class to another modulo class. This gives us a partial function, and we take the sum of all these partial functions to get a globally defined function, and we quite simply have something that maps the result of one homomorphism to the result of another homomorphism by conjugation. And to give a slightly more formal description of it, if we have k-leaf trees, we have our two ordered covering systems. We know how to compose linear maps. These are defined piecewise on modulo classes on the natural numbers, and well, the most natural description is, of course, in terms of a 2x2 matrix determinant. Okay, well, we have congruential functions. Alternatively, they're mappings between realizations of the dynamical algebra, or they map the results of one generalized conjunction to another by conjugation. So we get a special form of congruential function. So each element of an exact covering system is mapped to another modulo class. And we also see these turning up. So we see them in theoretical computer science. A paper by Burkle from 1994 also demonstrates computational universality in this setting, but we see them in terms of Conway's motivating examples. So Stefan Cole, 2017, a paper called the 3x+1 conjecture in a group theoretic context. So, of course, the operation from the 3x+1 problem isn't a bijection, but he gave a formulation of the same problem that was entirely based on bijections. In fact, congruential functions from this particular class. Sorry, one moment. So let's go back and look at the simplest possible example, rebracketing threefold conjunctions. So we've got three of them. We've got the unbracketed, we've got the right bracketed, and we've got the left bracketed. And this is where we discover that what we actually have here, well, from right bracketed to left bracketed, of course, we have the associativity isomorphism from linear logic. From the unbracketed to the right bracketed, this is where we discover the amusical permutation term. So we now have an interpretation for what this bijection is doing. And what it's doing is taking an unbracketed string and inserting a pair of brackets on the right. But it's one of a pair. So we have this other one that I'm calling the flattened permutation, and it takes an unbracketed string and inserts a pair of brackets on the left. And the two are related because this other thing that I'm calling the flattened permutation, the reason I'm calling that is because it precisely replicates Conway's amusical permutation, but one step down. So if we apply gamma to n+1, it's the same as applying gamma flat to n, then adding 1. So the orbit of 8 is infinite under the amusical permutation, if and only if the orbit of 7 is infinite under the flattened permutation, etc., etc. And this is, again, an example of what I'm talking about, transforming behavior of one function into another function by conjugation. So here, instead of an isomorphism, we have a partial injective function, which is simply the successor function. So the flattened permutation and the amusical permutation are simply related by conjugation by the successor function. And well, once we see this, we can start writing down some fairly simple algebraic properties. So we have rebracketing from right bracketing to left bracketing by deleting a pair of brackets on the right, so the inverse of the amusical permutation, followed by inserting a pair of brackets on the left, so the flattened permutation. We have, if we pass the successor function through the amusical permutation, well, what we have is the flattened permutation instead. And bringing these two together, we discover that actually the associator from linear logic, we can write it as a commutator, provided that we're happy to accept generalized inverses. So it's the commutator of the successor function and the inverse of the amusical permutation. But let's not forget that we've already given Richard Thompson's group F in terms of this associativity isomorphism. So what I'd like to do is take this associativity isomorphism and split it into two, into the inverse of Conway's A-musical permutation from the original Collatz conjecture, and the flattened permutation, which gives us just another way of writing the same conjecture. So instead of a 2-generator group, we get a 4-generator group. So it's generated by the A-musical permutation, flattened version thereof, identity and the A-musical permutation, identity and the flattened permutation, which is a fun thing to do. But the problem with this is that this group, there's so little we can say about it. It's quite remarkable, because saying almost anything non-trivial about it involves solving some very, very hard, possibly undecidable problems related to conjectures of Collatz. So I'm not about to give a presentation of this group simply in terms of generators and relations. But what I would like to do is to say that, well, we can go one further step, because we have a relationship between the A-musical permutation and the flattened permutation, which is that we derive one from the other simply by composing with the successor function and its generalized inverse. So what I'd like to do instead is say we're going to take not a group, but an inverse monoid. And this is going to be generated, the elements of this are going to be partial injective functions on the natural numbers. And what we're going to have is the successor function, and of course its generalized inverse, the A-musical permutation and its global inverse, and identity tensor both of these. And here we see that Thomson's group F arises as a subgroup of an inverse monoid. So it's a subgroup generated by commutators of generators. So the ones where we have the global inverse. When the inverse is globally defined, the commutators of the generators give us a copy of Richard Thomson's group F. Now, we can bring all this together, and instead of working algebraically, we can simply expand out the definitions. So we can write Richard Thomson's group in terms of the original Collatz conjecture and what Conway calls the A-musical permutation. And we can expand this out explicitly in terms of the A-musical permutation and adding and subtracting 1 in each case. And well, this is actually quite easy to check that we do indeed get a copy of F by simple elementary modular arithmetic. But I guess my point at this stage would be, it might be easy to check, but it certainly wouldn't have been easy to derive F from Collatz's conjecture without going through all the intermediates, logic, theoretical computer science, and implicitly category theory. So at this point, I will probably ask how much time I have left.
You have you have 5 minutes, 5 more minutes.
Okay. Well, very, very briefly then, I'll simply say that we could take this further. So if we were to take it further, we'd start looking at mappings between fourfold conjunctions. And we rely on the fact that our tensor, our conjunction, whatever you want to call it, is a monoid homomorphism. And this lets us build up homomorphisms explicitly that map between fourfold conjunctions by conjugation. And if we were to do this, well, this is where essentially we have to start considering category theory, because what we have around the outside here, the red pentagon, is known as MacLane's pentagon, one of the most famous commuting diagrams from category theory. And what we're doing when we're filling in the bits in the middle, well, the outside gives us Richard Thomson's group F, mappings between binary bracketings of 4 symbols. The maps from the outer to the inner, well, these are the bijections of Collatz, and these correspond to inserting or deleting brackets. And if we look at the inner pentagon, these give us mappings between partial bracketings. And this is part of simply a very, very long, in fact, sorry, an infinite series, I guess, of geometric figures based on bracketings of symbols, inserting and deleting brackets. This gives us the associohedra of Jim Stasheff, and I am quite happy to finish at this point, and thank you very much, everybody, indeed, for listening. Thank you.
Thank you, Peter. I think there were too many things in this 1 hour talk, and I think you give us a full round of almost all kind of algebra, all kind of arithmetical algebra, I would say, particularly the operas and then category theory. Anyways, it was wonderful, wonderful talk. Any questions from the audience? Anyone who come up with a question? Probably. Uh, okay, Peter, can you open the references in the beginning you mentioned?
Oh, sure. Hang on. Yeah. There. Okay.
Okay, particularly, I think the one who are interested in understanding these things, they can go with this reference. Peter, I was just curious about few questions, which are probably on a historical side. What George Cantor was doing in order to by using this particular the map you mentioned there.
Um, I mean, I think the point is that Cantor was, I mean, he wasn't working with trees, at least not explicitly.
Yeah, yeah.
But I mean, mixed radix counting systems, they've been around for a long time. In fact, there's sort of good evidence that counting systems were mixed radix before we ever sort of fixed on a single base. So you've got the units for time, sort of 60, 24, all that kind of thing.
Mm-hmm,
So
mm-hmm,
yeah, so Cantor, who originally gave the formula for actually taking something written down in a mixed radix system, working out what particular number that was, I guess.
mm-hmm.
We've got the same in the sort of pre-decimal British currency, where you had, I don't know actually, sort of you had sort of base four somethings to the penny, a certain number of 12 or 20 pennies to the shilling, 20 shillings to the pound, all that kind of thing.
Mm-hmm.
So American units for measuring distance, that kind of stuff. They also have a very 12 inches to the foot. I don't know how many inches to the mile, but if you wanted to know, you'd have to sort of use Cantor's formula to work it out.
Mm-hmm. Okay. And secondly, I was just curious about when Conway was trying to build that particular fractions. So whether there was any motivation that he took from Stern-Brookert sequences in order to write down all the fractions. Stern-Brookert
Sorry,
sequence.
sorry, what sequence? Sorry, I missed that.
I dropped in the message of the chat. You
Hang
can
on,
see
I'll see if I
stun brokered sequences.
can. That's. Let me call up the chats. Okay. Okay, that's. I wouldn't even presume to try and reply. Okay, I
So
don't know. That's a very, very good question. I don't know the answer.
okay. Okay, and if you summarize what John Conway was trying to say through the undeterministic of a particular sense in what you try to explain in the whole talk, the John Conway's point of undecidability.
Yeah. So John Conway's point of undecidability. Um, I mean, I guess what he's really showing is, so where are we? Yeah, so what he's really showing is sort of, I mean, we sort of know that theoretically that undecidability is a possibility in mathematics, but I mean, he sort of demonstrated that it didn't have to be anything sort of obscure or esoteric. I mean, we see sort of undecidability turning up in sort of complicated logical systems before that. But really, he demonstrated that sort of even in sort of the most simple arithmetic problems, we have undecidability as a possibility, and sort of neatly related it to a class of problems that are very, very closely related to Collitz's conjectures. So that's essentially my take on that. We already knew undecidability was possible, but he demonstrated sort of how ubiquitous it was, how it sort of turned up everywhere, kind of thing.
But if one talk about the classical geometry problem, the fifth postulate of the Euclid, which is declared that that is one of the problem which can't be proved, which has no proof and can't be proved. So can we say similar thing regarding to Collard's conjecture on the basis of what John Conway has been trying to prove, trying to say?
I mean, that would be a lovely research project. I certainly can't answer that off the top of my head, but okay. The quick answer is I would love to see someone do that. I'm not aware that it's been done. I would love to see if someone has done it. Yeah.
Particularly, this would be an approach towards the NP-hard problems, particularly how to address those problems, and probably categorizing in the similar way a undeterministic behavior that, okay, the statement might be true, but it can't be, it can be undecidable. I don't know, but these are some wild thoughts out of it.
This wild thoughts become research projects. This is good.
Yeah. Probably anyone else who come up. Thank you, Peter. Thank you for answering my wild questions. Anyone else who would like to ask anything or share any comment in the audience? Probably. Okay. If this is the case, let us thank the speaker once again. Thank you, Peter. This is wonderful talk. We are going to place the recording of this particular talk, and anyone who would like to have any questions, probably they need to rephrase it. And if you want to write, you can write directly to Peter. His email address is written on the bottom of his slide. You can see that peter.hines@york.ac.uk. And I tried many times. He's very quick in answering the questions, answering the emails. You can try as well. Okay, Peter. Thank you very much, and
good to
thank
speak to
you
you again. Okay.
I hope we will have you again with many interesting stories and talk. Thank you very much. Thank you, everyone.
Cheers then. Bye.
Bye.